All right, guys, so here is nuclear chemistry part 2 continued, I guess is how we want to put it out there. So I feel like I went through this problem really quickly, so I'm going to back it up for a minute and just review this problem, and then we will move on to the last few slides. Okay, so we talked about alpha and beta, right? We talked about the symbols. We talked about alpha. If it's a particle that releases, or an atom that releases alpha particles, it's only going to release alpha particles. If it's an atom that only releases beta particles, it's only going to release beta particles. The exception to the rule is going to be gamma. So if there is an atom that emits gamma particles, it can emit gamma and alpha, or gamma and beta. Okay, so there can be a mix if it is an atom that gives off gamma particles. So let's go back to this problem down here below. We have uranium. Mass number here is 238. The atomic number, which is the subscript, is 92, which gives us the indication that it is uranium. And if you look, uranium undergoes gamma decay and alpha decay. That means that it's going to give off both. So in terms of our notation for our equation, the gamma particles, since it does not have any mass or any charge, it just needs to be represented in the equation, but is not going to affect anything else in the equation. In terms of alpha particle given off, you know that with alpha particles, our proton number is going to decrease by 2, right? Indicated by the charge here. But then you also know, because of the alpha particle having a 4 as its mass, then we're also going to decrease this mass number on the top. So we end up with 238 minus 4. So we end up with 234 as the superscript for this element. Then we have 92, and we are going to subtract the 2 in terms of charge. That means that our 92 now becomes a 90. Since the element that we're talking about is determined by the atomic number, if you take a look at your periodic table, you will see that 90 now represents thorium, which means that uranium underwent alpha and gamma decay and basically converted into thorium based on the principles we know about radioactive atoms. Okay, so hopefully that was a little bit clearer. Okay, so now I want to talk about some general concepts. So we're going to talk about positrons, we're going to talk about electrons, captures, and then we're going to talk about neutrons, capture and emittance. So let's get started with positrons. So the important part of this is, how do you write a positron in an equation? So to write a positron in an equation, you're going to have a lowercase e, right? The mass number is going to be 0, and then your charge is going to be 1. So things that I want to remember when you guys are doing these problems, really important, is to realize what side of the equation that you should put these things on, right? So for positrons, if they are emitted, the number of protons is going to decrease. I want you to remember certain key words. So emitted means that it's going to be on the product side of the equation. And we're going to go through a whole set of nuclear decay problems, and you guys will hopefully get the hang of it by the end of that. The second one is, if electrons are captured, first of all, you're going to make your notation for an electron. You're going to have a lowercase e. The superscript is going to be a 0, and then your subscript is going to be a -1. Okay? What I want you to think about is up here, right? The number of protons is going to decrease, but if you look at the notation, the mass number here, or the mass, is 0, and the charge is 1, as opposed to if it's an electron, the mass is 0 and the charge is -1. Okay, so if an electron gets captured, the number of protons will also decrease. Now, the big difference is, if something is captured, then it will be on the reactant side of the equation. It means that it took it in. It needed it for the reaction to happen. In terms of emitted, the reaction happened and then it was given off at the end of the reaction. Okay, so I want you to be very clear about those words, because when you guys are reading these problems, that's what you're going to see. You're going to see a positron was emitted. You need to know that the proton number is going to decrease, and then you need to know that if it's emitted, it's going to be on the product side of the equation. Okay? All right, so in terms of a neutron, when a neutron is captured or emitted, you're going to be using this symbol to represent it in the equation. So it's going to be a lowercase n, and then your mass number is going to be 1, and then your charge is going to be 0, which should make sense, right? Because a neutron doesn't have any charge, but it obviously has a mass, so it's going to contribute to the mass number, but not the actual charge, okay? So key things from this slide. Remember, positrons are notated with a superscript of a 0, a subscript of 1, and a lowercase e. If it is emitted, the number of protons are going to decrease, and you're going to put this symbol on the product side of your equation. In terms of electrons, if they are captured, you're going to notate it like this. You'll put a lowercase e. Your mass number will be a 0. Your subscript or your charge will be a -1. If it's captured, that means that it's taken in for the reaction to happen. The proton number is also going to decrease, but you're going to put that electron notation on the reactant side of the equation. And then in terms of a neutron, we'll go through some of these problems so it'll make a little bit more sense later on. But if it is captured, that means that it's going to be on the reactant side. If it's emitted, that means it's going to be on the product side. And then we're going to use this symbol here, which is the lowercase n. The superscript is going to be 1, because remember, the neutron will contribute to the mass, but the subscript is going to be 0 because the neutron does not contribute to charge. Okay, so what I did for you is I actually put together a little table for you. Okay, so I'll just summarize the table for you. Right, so if you see the word emits, undergoes, or decays, that probably means that you're going to put whatever the notation is on the product side for the particle. In terms of capture, if you see the word capture in the question, that normally is going to mean that it's going to be on the reactant side. You needed to capture that energy or that particle for the reaction to happen. In terms of the symbols, we've gone through this many times, but one more time won't hurt. Alpha particle, if you're looking at it right, superscript is 4, subscript is 2. Remember, top is mass, bottom is charge. For beta, how you're going to write it in your equation, the upper number or the subscript is going to be 0. The superscript is going to be 0. The subscript is going to be -1, and then you're going to use your fancy B. If you see emits, undergoes, or decays, it's going to be on the product side, and the number of protons is going to increase. And let's back up for a minute. On the alpha side, right, if you see emits, undergoes, decays, that means it's on the product side. And in terms of what you should be writing in your equation, the number of protons are going to decrease, okay? So alpha decay, number of protons decrease. Beta decay, the number of protons increase. There is no really fancy trick to try and remember it. I'm hoping that as you guys practice some problems, it'll be a little bit easier to remember. Okay, so let's move on to gamma. For gamma, remember, it does not contribute any mass. It does not contribute any charge. If you see something with emits, undergoes, decays, it's going to be on the product side. If it's by itself, it's not going to change anything, right? Because it does not contribute to mass. It does not contribute to charge. But the big thing is that gamma radiation can be emitted or given off with other types of radiation. So you may see a problem where it says this atom undergoes gamma and beta decay. Okay, and it'll be up to you to figure out how to write that depending on what you see in the problem. Okay, so let's take a look at the 3 that normally are a little bit confusing to kids, and it looks like I actually, excuse me for a second while I fix this notation. It looks like I thought that a neutron right here would be an E, but nah, it is definitely an N. So I'm going to change that right now. So let's back it up and let's take a look at what's going on here. Okay, so in terms of a positron, when you have a positron and the symbol that you're going to use in your equation is going to be a lowercase e, and then you're going to have a 0 because it does not contribute to mass, but you're going to have a 1 down here, meaning that it's going to contribute to charge. If it is emitted, undergoes, decays, remember keywords, it's going to be on the product side. The number of protons is going to decrease, right? And then if we talk about the electrons here, the notation is quite similar, right? We have the upper number here, or the superscript, which is a 0. Then we have the subscript, which is a -1. We're going to represent it with a lowercase e. And if it is on the reactant side, you're going to see a word like capture. That will let you know that it belongs on the reactant side. So if it's on the reactant side, that means the number of protons is going to decrease. And then last but not least, we have neutrons. Remember, neutrons have no charge, so it's going to be 0 under charge because it won't contribute to charge. But it does contribute to the mass, so that's going to be a 1. If you see emits, undergoes, decays, that means it's going to be on the product side. That means that the number of neutrons is obviously going to change. And then on the reactant side, you're going to see something like captured, and the number of neutrons, once again, is going to change. So the reason why I left those kind of, let's say, vague for right now is because you have a whole worksheet to go through. And hopefully by the end of that, you will be an expert in how to write these equations. All right? So hopefully that was helpful. And that is it for your nuclear chemistry notes. On to nuclear decay problems. Bye! See you later.